This is part 2 of the friction lab. In doing this lab activity, I was overly cautious and cleaned the track, which left a residue on the track, which dropped the coefficient of friction from what I'm normally used to. If you watch the video, there may be some slight changes in the data that you see here. I did go back and redo a few of the trials that I was unhappy with because of the challenge of the track being too clean. But what that ultimately meant was that the coefficient of frictions have dropped a little bit and are a little bit closer than I like and I normally have. But the results of the data still are going to come out and show the trends that we expect to see. So in doing the lab, what we collected was the mass of the block and the hanging mass. Tables A1, B1, B2, these tables here are all going to be the same. Table C, we're going to have to make some different calculations, but the calculations in all of these tables are going to be the same. And so when we're dealing with the mass of the block, what we have is we have a block sitting on a counter. We have a pulley here. The block is getting pulled on by a hanging weight. So there's a force here. We'll say this is the applied force of the hanging weight, which is equal to mg of the hanging weight. And so that is what goes into these cells here. We just take the hanging mass and we multiply by 9.8 and we get these values. I strongly encourage you to let Excel or Google Sheets do the heavy lifting for you. Do the equation once and then autofill down. Copy the equations from table A into table A1 into table B1, so on and so forth. But in this particular case, to find the applied force, you're just going to take the hanging mass times gravity. You then are going to have a frictional force that's created. The frictional force is equal to the normal force. Since this is a flat surface, the normal force is equal to the weight of the block, which is mg. And so you can find the normal force. And so and that means that the frictional force would equal the mass of the block times gravity times mu. Cosine of 0 is 1, so we just drop that, but it's the mass of the block times gravity times mu. We don't know mu. What we do know is that at the point where this releases, the force that is located in the forward direction and the force that's located in the backwards direction are equal and opposite. Thus, the applied force and the frictional force are the same. To figure out the normal, again, that was right here, that's your mg. If they are equal and opposite, what we discover is that mg, the hanging weight, is equal to m, the block, times gravity times mu. And you can then solve for mu. So you can solve it and get mu is equal to m hanging times gravity divided by m block divided by gravity. The gravities cancel out, so the hanging mass divided by the block's mass in this case is equal to mu. So you can get that value here. And again, if you let Excel do the heavy lifting or Sheets do the heavy lifting, it will autofill down for you. Then we take the average. So we just do something like average and then select all of these cells. So it would be A, B, C, D, E, F. F2 to F4, and then it will auto-calculate for you. The equation for the cell at the top would be something like, if this is A, this is B, C, D, E, F. It would be something like, for mu-s, it would be the hanging mass, which was C2 divided by B2. For the normal force, it would be something like the mass of the block, so B2 times 9.8. And you just put these in and then autofill them down. And so those equations will get you the values for these tables. For this table, we have to get our value a little bit differently, because what we have here is our inclined plane, and the inclined plane has a parallel force on it acting this way and a frictional force acting this way. And so the equation for the parallel force is mg sine theta. The equation for the friction is going to be mg cosine theta times mu. And so they're going to be equal and opposite. Again, some of the forces adds up to 0. They cancel out. And so you would get mg cosine theta mu is equal to mg sine theta. The parallel force is equal to frictional force. The m's and the g's cancel out. You're left with cosine theta mu is equal to sine theta. And so theta is equal to the arc tangent, or is equal to the tangent, I'm sorry. The arc is equal to the, so let me do that again. I misspoke there. So you would have mu is equal to the tangent of theta. And so if I have the angle, I can plug it in and I can get mu. So the tangent of 12, the tangent of 13, tangent of 12, the mass canceled out. It was irrelevant. And so the angle is all that matters. And so these mu k values should be the same, and the angles should be the same. They aren't exactly the same. It was difficult here getting those because half a degree, it's challenging to read. So that has a big difference. So that is how you find your mu value, is you take the tangent of theta. To do that in the computer, you would do something like the tangent of, again, A, B, C, D, E, F. So you do something like the tangent of C. I don't know what cell this is. This is, I'd be like 20 or something like that. It's a lot more than that. C20 divided by 57.3 to put it into radians. That's approximation. If you want to really convert it, you would have to do something like C20 times 180 divided by capital P, capital I, open close parentheses. And that gives you your conversion. But I'll let you do the 57.3 degrees here, which is 180 divided by pi rounded to the 10th. And that will get you your angles, your coefficients of friction. Now, from there, you will go and analyze this data in your lab report. If you have any questions, please let me know.